Greetings, friends. My name is John Gabriel, and this is the New Calculus channel. Today I'm going to be speaking to you about some of my earliest job experiences, and these took place back in the 1980s, when a lot of the stuff that you see in front of you here was not even around then. In fact, I'm going to talk about a project that I worked on where I had to optimize code for combat aircraft, and it was very tricky for several reasons. So in any case, let's begin without further ado. Now, to improve the execution speed of the code I was writing, I had to figure out a way to use less conditionals because real-time data was being parsed thousands of times every second and used to control other equipment or ordnance. So I've actually written an article here, which I'll place a link to, and you can read it in your own time. And what it had to do was basically determine very quickly, for example, things like when a missile or ordnance can be released, and it had a lot of real-time data to consider, things such as aircraft speed, altitude, wind speed, target tracking, missile lock status, and many other relevant data. So given so many real-time inputs, you have to think about the number of conditionals. And if there are many of them, it can end up being unusable because it's just too slow. Imagine, for example, the disaster that would follow if a guided missile ignited while still attached to the undercarriage of a wing or part of the aircraft. So the guided missile must only ignite once it is completely detached from the wing and at a safe distance. Okay, so things like this are very important in these real-time systems, and there are lots of other things that come into consideration here. So I'm going to talk about them briefly. Back in the 1980s, many inputs took the form of transcendental trigonometric functions, okay, that are very processor intensive. So what this means is that the processors, which were miserably slow, had to do floating point calculations and often had to be replaced. The floating point library often had to be replaced by a math coprocessor, which was a lot faster. But even then, it was still very slow back then because, the processors back in those days were just really, really slow, okay? And of course, memory was at a premium, and disk space was at a premium, and things were just really so slow that you had to do everything very carefully if you wanted it to work. So long before object-oriented languages appeared on the scene, programmers like me were striving to write object-oriented code. Even in languages such as assembly x86, believe it or not, you can do it. So for example, it's possible to write object-oriented code similar to what you have in C++, which came much later, or many years later. For example, a jump table in assembly x86 is like a table of pointers to functions in C or C++. So it was from this idea that I managed to compile a vector table which would replace all the conditionals. So there was not a single conditional with all these inputs coming in. And that drastically improved the execution speed. But it's not as easy as it sounds because due to lack of sufficient memory, the index couldn't be as large as, for example, the number of inputs that you had, and also those that would not fire a particular function. So one had to be very clever with these indexes so that you could shrink them down and take up as little space as possible. So I found a question on the internet about this very topic. Some students were working on a lab assignment, and they had 5-letter grades which were associated with a number range. And they wanted to be able to print out one of those grades given a floating point value, and they didn't know how to do it. So this is a very simple task compared to what I had to do in my job. And unlike those students, if I didn't deliver, I would probably not have a job. So I knew of no other person before me who had done it. And I couldn't turn to anyone and ask for advice because there wasn't anyone to ask. In fact, even many years later, when I tried to do a course, tried to complete my BSc in computer science at University of Cape Town, the idiots in that department wanted me to redo the first year, which I had already done at a previous university. So in any case, cut a long story short, fools only figured out these things many years later. And so now it's very easy to do this. You can basically get the grade, set up a vector table to be indexed by the integral grade, and then you can basically just spit out. This stuff here is done before. All these for loops is done before you actually get to the important point, okay? And so then you simply index the vector table with the integral grade. So I'm not going to carry on with this article because I wanted to show you something on the internet. So there is a free compiler where you can use any particular one that you like, C or C++, whatever. And so what I've done here is I've wanted to show you some of the things that I had to do in assembly. Now this code was not available back then. There wasn't even C available. But C is really a high-level assembly language. So if you look at, for example, an integer array, such as the one I'm showing you here, what happens is that the compiler will actually store memory for it. And array, in fact, happens to be a pointer to integers, okay? And it's very much the same as this declaration here, with the exception that it can be offset either using brackets or in a special way, as I've shown here. And I've done this on purpose, incidentally. I've put the I outside the bracket because the compiler doesn't care which one comes first. It does care, though, if you try to put something after the bracket. So you can't really, for example, have the I on this side of the array. And all this code, by the way, is shown. I disassembled the program to prove to you that there are no if statements. And if you look at all of these here, none of these instructions are doing any testing for conditionals. So for example, move SD moves data from string to string. The second one converts a double precision floating point, and the FLD loads a floating point value, etc., etc. Okay, so all these things here, you can actually just type in the directive followed by assembly in Google, and it will tell you what these things do. All right. So coming back to this little illustration here, there are all these things that you see here. All these 1, 2, 3, 4, 5, 6 are all equivalent ways of accessing the fifth member of the array, because array subscripting and string subscripting in C and C++ and in assembly starts at 0, okay? So if you had to say array 4, that means the fifth element, right? So, and then of course you can print it out either like this or by using the actual array name followed by the brackets, or in any of these 5 ways. You can actually do these things. And so now, what is the difference between k pointer to int? So if you have a k pointer which points to an integer, then you can assign it the value of an integer variable by passing its address. That's what this ampersand does. It passes the address of k to store in k pointer. And so when you want to actually access the value of the integer, you access it with a parentheses, star, and parentheses. Now, what is a pointer really, very quickly in C and in assembly? So a pointer contains some memory address, okay, because obviously you have, in the hardware, you have memory addresses which are accessed via instruction pointer. And so they can be either random values or null if initialized. And of course, an array name is a pointer that contains the address of the array indexed by 0. So a memory address varies depending on the architecture of a processor, and in x86 assembly language, a pointer consists of an address, segment, and an offset. So this was even harder back in those days because we couldn't say, for example, do a statement like move SD easily, or we did have LEA because normally the segment was 16 bits and the offset was 16 bits, but later on the addresses were stored in double word integers or double word integer form. So the following statement declares an integer array and allocates space for it on a local stack, this statement here, okay, because it's part of main. If it was outside, then it would be stored in a different location, probably in the data segment, but the compiler may not necessarily initialize the array, and usually it doesn't. Okay, so you have to be careful of those things. You can't assume that it's 0. In any case, so this is what I ended up doing many years later, writing C and C++ programs. I've written device drivers, I've written firmware, I've written high-level GUI applications, and of course, all that, quote, fun damaged my eyes, and especially my right eye. I can't really use it very much. There's no way I can do software development full-time. But I can tell you this, I was at the top of my field. I've never met anyone who could write algorithms as well as I could. And one of the secrets of writing good code is not only being able to design an algorithm, having a deep knowledge of mathematics, but learning how the compilers or interpreters work. Okay, so a programming language is a programming language is a programming language. Once you know one, you can basically figure out the rest. So I didn't choose to go into programming for any other reason except the remuneration. I found out that by writing code, I could earn a lot of money, and I needed money in order to travel. So that's what I did earlier on in my career. I had first planned to be an actuary, and then I found that to be pretty boring, and it wasn't paying as well in the beginning, simply because I guess I wasn't yet qualified, and probably it would have paid better if I did obtain the qualification, but it wasn't really something that I found interesting. And eventually I decided I'm going to do programming full-time because it was more interesting, but still not my first choice. I really wanted to teach, and of course, teaching back in those days, you wouldn't really earn enough money to pay your bills, so there was no way I could go into teaching. But many years later, I did, and that was my real calling, to teach. I'm able to devise exemplary teaching strategies to many different types of learners, but especially constructive individuals. Okay, so I'm not going to spend more time on this. I've rambled on and on. So there you've learned a little bit more about me and what I did earlier on in my career, and you have a better idea now of some of my background. I'm John Gabriel, this is New Calculus, and hopefully in the next video we'll have another interesting mathematics topic. Till next time, goodbye.